Hello, my dear students. Today we are going to discuss analog to digital conversion of the subject data acquisition system and microprocessors. Data acquisition systems and microprocessors. First question is explain the basic concept of A to D converter. And then you can ask what are the A to D converters. A to D conversion system is that the input it will take in the form of analog form, that is in the form of sine wave. Any kind of signal we can apply, or any electrical signal we can apply which is in the form of sine wave, that is converted into equivalent of binary digits, or that is equivalent to in digital form. You can see how you can represent that analog to digital conversion or A to D conversion. So an ideal A to D converter takes an important analog voltage and converts to a perfectly linear digital representation of the analog signal. If you are using if you are using if you are using a 8-bit converter, the binary representation is 8-bit binary number which can take on 2 raised to 8 or 256 different values. If your voltage range were 0 to 5 volts, then 0 volt is equal to 0 0 0 0 0 0 0 and 5 volt equal to 1 1 1 1 1 1 1 1. Next, what are the applications of A to D converters? Microphones. Take your voice varying pressure waves in the air and convert them into varying electrical signals. Strain gauges determines the amount of strain, or you can say change in dimensions when a stress is applied. Next, thermocouple, temperature measuring device, converts thermal energy to electric energy. Voltmeters, digital multimeters, these are the some applications of A to D converters. Then list the specifications of A to D converters. List the specifications of A to D. In that, monotonicity means that the magnitude of the output voltage increases every time the input digital code increases. Absolute accuracy is the measure of the DAC output voltage with respect to its expected value. Then resolution. This is very important specification for the exam point of view. The number of bits used to represent the analog signal. Increased resolution is equal to increased precision. You can see how the resolution is increased. LSB, the smallest step size achieved. 1 LS is equal to full scale upon 2 raised to n. Next specification is relative accuracy, is the deviation of the actual from the ideal output voltage as a function of the full scale voltage. Settling time is the time required for the outputs to switch and settle within half LSB when the input switches from all zeros to all ones. Next, differential nonlinearity is the difference between actual and expected step size when the input code is changed by 1 LSB. Is the offset error occurs when the DAC output is not 0 volt when the input code is all zeros. Next, gain error occurs when the output states before reaching the maximum output code. Linearity error is the deviation from a straight line output with increasing digital input codes. Then list the types of ADCs. List the types of ADCs: flash type ADC, delta sigma ADC, dual slope or integrating ADC, successive approximation ADC, and counter or ramp type ADC. One more is counter or ramp type ADC. In that, first one is successive approximation ADC, or explain successive approximation type ADC. Successive approximation register SAR is added to the circuit instead of counting up in binary sequence. This register counts by trying all values of bits starting with the MSB and finishing at the LSB. The register monitors the comparator's output to see if the binary count is greater or less than the analog signal input bits accordingly. Next, this is the successive approximation ADC circuit. SAR, D to A converter, and some storage registers are there. Then you will get output like this. So the whatever unknown voltage, analog voltage is there, that is successively approximated with the some amount of voltage. When successive approximation register will stops, or when analog voltage is nearly equal to the approximated value of voltage, that is nothing but a analog equivalent of digital output. Then what are the advantages of successive approximation? Advantages are capable of high speed and reliable medium accuracy compared to other ADC types, good trade-off between speed and cost, capable of outputting the binary number in serial format. Then what are the disadvantages of successive approximation type ADC? Higher resolution successive approximation ADCs will be slower, speed limited to 5 Mbps. These are the some advantages and disadvantages of successive approximation type ADC. Then explain flash type ADC. Flash type ADC consists of a series of comparators, each one comparing the input signal to a unique reference voltage. The comparator outputs connect to the inputs of binary encoder circuit, which produces a binary output. So this is the flash type ADC circuit. So here number of comparators are 8. Number of comparators are 8. So you can go through the 8 different reference levels. Then how it will work? As the analog input voltage exceeds the reference voltage at each capacitor, the comparator output will sequentially saturate to high state. The priority encoder generates a binary number based on the highest order active input going all other active inputs. So this is the output of flash type ADC, analog input, and the digital output is in stepwise. Then advantages of flash type ADC: simplest in the terms of operational theory, most efficient in terms of speed, very fast, limited only in terms of comparator and gate propagation delays. Disadvantages: lower resolution, expensive. For bit, the number of comparators is doubled, that is for 8 bits 256 comparators needed. Next is explain dual slope ADC. Explain dual slope ADC. So this is the circuit diagram of dual slope ADC. It is having integrator, comparator, logic circuit, counter and latch. A slightly more sophisticated design known as dual slope integrating ADC eliminates most of the problems encountered when using the single slope converter. Here two integrators are performed, one on the input signal and one on V reference. The input voltage in this case is assumed to be negative, so that the output of the inverting integrator results in a positive slope during the first integration. So you can see why it is called a dual slope. So whatever slopes you will get, one from unknown measuring voltage, another is from 1 minus V reference voltage. So first slope is fixed integration period, second slope is variable integration period, that is T2. Above figure illustrates the behavior for two separate samples. The first integration is of fixed length dictated by the counter, in which the sample and hold signal is integrated, resulting in the first slope. After the counter overflows and is reset, the reference voltage is connected to the input of the integrator. Since Vin was negative and the reference voltage is positive, the inverting integrator output begins discharging back down to 0 at constant slope. A counter again measures the amount of time for integrator to discharge, thus generating the digital output. Notice that the first slope varies according to the value of the input signal, while the second slope, dependent only on V reference, is constant. Similarly, the time required to generate the first slope is constant, since it is limited by the size of the counter. However, the discharge period is variable and results in the digital representation of the input voltage. So here the advantages of dual slope ADC: resolution able to achieve 14 bits or higher, very inexpensive to produce, low power consumption, very low offset and gain errors, highly linear, good noise performance. So here the disadvantages of dual slope ADCs are slow conversion, typically less than a few hundred samples per second, sensitive, direct dependence of the digital output to the values of resistor R1, capacitor C1, negative reference voltage V reference. So here the next question is for comparison between ADCs, performance comparison between ADCs. So you can see in the picture, dual slope, speed is slow, cost medium, flash type very fast, it is having a speed and cost is high. Successive approximation, speed is medium as well as fast, the cost is low. Sigma delta, slow and cost is very low. Next, comparison of ADCs. So integration type, successive type, flash type, sigma delta. Speed is slow, successive approximation fast, flash ADC fastest, sigma delta slow. Noise, integration type ADC rejects, not eliminated, not eliminated. Sample and hold device, not required, required, not required, required. Resolution of integration type ADC high, medium to high, low resolution, high resolution. Cost is integration type low, successive approximation modest, flash ADC high, and sigma delta is low. With this, here we will complete the fourth chapter of that is analog to digital converters of data acquisition system and microprocessor, which is having 30 marks, and this is very important chapter for the exam point of view. Please go through this. Thank you.